Bismillahirrahmanirrahim. Assalamu alaikum. Welcome to the 12th lecture of Mechanics of Solids. Today we'll continue our discussion on bending from the previous lecture. In today's discussion, we'll develop the core principles of bending and we'll discuss one of the most important formulas of the mechanics of solids, that is the flexural formula. And after that, we are going to discuss some of the examples on how we can practically apply the flexural formula to solve bending problems. In this discussion, we will discuss the deformations that occur when a straight prismatic member made of homogeneous material is subjected to bending. This discussion will be limited to beams having the cross-sectional area that is symmetrical with respect to an axis, and the bending moment is applied about an axis perpendicular to this axis of symmetry. You can see here that we are having a prismatic member in which we have an axis of symmetry, that is the y-axis, and bending moment, or you can say this curvature, is being applied perpendicular to this axis of symmetry. The behavior of members that have unsymmetrical cross-sections or are made from several different materials is based on similar observations and will be discussed separately in later lectures of the series. By using a highly deformable material such as rubber, we can illustrate actually what happens when a straight prismatic member is subjected to bending moment. For example, we have an undeformed bar which has square cross section and is marked with longitudinal and transverse grid lines. When a bending moment is applied, it tends to distort these lines into this kind of pattern. You can see here that horizontal lines become curved. However, the vertical lines remain straight, yet they are a bit rotated or at an angle from their initial position. They are still straight, but they are at an angle. You can see here from their very straight position. The bending moment causes the material within the bottom portion of the bar to stretch and the material within the top portion of the bar to compress. Consequently, between these two regions, there must be a surface that is called the neutral surface, in which the longitudinal fibers of the material will not undergo a change in length. From the observations made on the previous slide regarding the distribution of tension and compression within the cross section, we can make the following, or we can make three assumptions regarding the way the stress deforms a material. First of all, the longitudinal axis x, which lies within the neutral surface. For example, here this is the neutral surface and this is the longitudinal axis x that was lying within the neutral surface, or here you can also see this in this figure, that this longitudinal axis x is lying within the neutral surface. It will not experience any change in length when a deformation occurs, when the bending deformation occurs actually. So this is our first assumption. The moment will tend to deform the beam so that this line becomes a curve that lies in the xy plane of symmetry. So this line will become a curved line, but it will not change in length. It will like change its angle but not length, and it will lie actually in this xy plane of symmetry. Then all the cross sections of the beam remain plane and perpendicular to the longitudinal axis during the deformation. The plane sections that were like originally plane, they will remain plane even after the deformation, and they will be actually perpendicular to this curved axis or curved line. And third, any deformation of the cross section within its own plane will be neglected. In particular, the z-axis lying in the plane of the cross section and about which the cross section rotates is called the neutral axis. So any kind of deformation that is occurring within the plane of the cross section, or actually this YZ plane, will be neglected. We are only considering the deformation that is occurring in this XY plane. In order to show how this distortion will actually strain the material, we'll have to isolate a segment of the beam located at a distance x from the origin, or from, like, if we are considering this end of the beam as origin, then we'll have to consider this small segment of thickness del x, and we'll see how this distortion will actually strain the material by considering this small segment in the next slide. Okay, so this slide needs an extra bit of focus. We are considering the segment del x that we originally recognized in the beam, in the deformed beam, in the undeformed as well as the deformed state. So this is the segment in the undeformed state. We can see here that the difference between undeformed and deformed state is that any segment above or below the neutral axis changes its length in the deformed state, but the we can say the length of on the neutral axis remains the same. This del x is same as this del x, but this del x, del s, which is actually located above the neutral axis, has contracted, and it is now del s dash. So if we want to find the strain at this particular location, we can find by using the simple formula of strain, that is del s dash minus del s divided by del s, and just apply the limit, and we have the strain here at this location. If we want to represent the strain in terms of the location y from the neutral axis and the radius of curvature rho, because this is actually bending, so we have a radius of curvature here. So what we are basically saying is that before deformation, actually this del s is actually equal to del x. After deformation, del x has a radius of curvature rho with center of curvature at point O dash somewhere. Since delta theta defines the angle between the sides of the element, del x is equal to del s is equal to rho into del theta. What we are basically trying to say is that in the original configuration, since del x and del s were equal, and even in the deformed configuration, del x is actually equal to rho into del theta, so del s is also equal to rho into del theta. We are here applying simple formula of the circle that says that s is equal to r theta, where s is the perimeter of the circle, r is the radius, and theta is the angle of that segment that we are basically considering. So now in the next step, the deformed length of del s becomes del s dash, and this del s dash is actually equal to the rho minus y. You have to subtract this length here. Y is the distance from the neutral axis to this length into del theta. So if we substitute these equations of del s and del s dash in this strain equation, we come up with this equation for the strain, this limit with this limit being applied, or simply we have this relation here because p del theta minus p del theta just cancel, and we are just left with minus y over rho. Sorry, this is not p, this is rho, and thus we are just left with minus y over rho, or minus y over this hypothetical radius. This important result indicates that the longitudinal normal strain of any element within the beam depends on its location y on the cross section and the radius of curvature of the beam's longitudinal axis at the point. In other words, for any specific cross section, the longitudinal normal strain will vary linearly from with y from the neutral axis. A contraction will occur in fibers located above the neutral axis if we have positive bending. Just remember this thing. Whereas elongation will occur in fibers located below the axis. This variation in strain over the cross section is a representation of basically the basic bending formula that we'll derive in upcoming slides. So here we can see in this figure that the strain is varying from the neutral axis. It is in compression above the neutral axis while this section is in tension below the neutral axis. The maximum strain occurs at the outermost fiber located at a distance of y is equal to c from the neutral axis. Since maximum strain is equal to c by rho from the similarity of triangle, we can find we can come up with this formula for strain at any location along this axis. So y over c is the distance from the neutral axis to the maximum or to the outermost fiber. Y is the location to the distance to that particular location where you find the strain, and E maximum or the maximum strain you can determine that using this formula. This normal strain depends only on the assumptions made with the regards to the deformation. When a moment is applied to the beam, therefore, it will only cause a normal stress in the longitudinal or x direction. All the other components of the normal and shear stress will be zero. It is this uniaxial state of stress that causes the material to have the longitudinal normal strain component Ex. Furthermore, by Poisson's ratio, there must also be associated strain components in the y and the z directions. However, we have neglected these deformations. Such deformation will cause the cross-sectional dimensions to become smaller below the neutral axis and above the neutral axis. The dimensions will become actually larger. For example, if the beam has a square cross section, it will actually deform in this shape, but these effects are secondary and negligible. Thus, we do not consider these effects in the normal derivation of flexural formula. Now we will develop an equation that relates the stress distribution in a beam to the internal resultant bending moment acting on the beam's cross section. To do this, we will assume that the material behaves in a linear elastic manner and therefore a linear variation of normal strain must then be a result of a linear variation in normal stress. Hence, like the normal strain variation, stress will vary from 0 at the member's neutral axis to a maximum value sigma max, a distance c furthest away from the neutral axis. Because of the proportionality of triangles, by using Hooke's law, we can determine this relation in the similar manner that we have actually determined for the strain on the previous slides. So, stress at any particular location above the neutral axis can be determined using this relation between maximum stress and the distance from the neutral axis. This equation is basically describing the stress distribution over the cross-sectional area. The sign convention established here is significant. For positive bending moment, which acts in the plus z direction, as in this figure, positive values of y give negative values for stress. That is a compressive stress since it acts in the negative x direction. Similarly, negative y values will give positive or tensile values for stress. If we select a volume element of material at a specific point on the cross section, only tensile or compressive normal stresses will act on it. For example, you can see here that this small element located at a distance y from the neutral axis have only compressive stresses acting on it. We can locate the position of the neutral axis on the cross section by satisfying the condition that the resultant force produced by the stress distribution over the cross-sectional area must be equal to 0. Noting that the force is actually dF is equal to, or the differential force is actually equal to stress into differential area. This acts on the arbitrary element of area dA. The resultant force or the summation of force basically requires that if we take an integral of this whole force and the stress distribution, like integral of on the both sides of this equation, we come up with this situation here where this maximum stress is actually a constant value, and this C, or the location of the topmost fiber from the neutral axis, is also a constant. So we can take these two values outside the integral, and we are left with this integral by dA. Now we are having this situation here where either this term must be equal to 0 or this term, but we know that the maximum stress and the and this fractional term cannot be equal to 0, maximum stress over the location from neutral axis to the topmost fiber, so this term must be equal to 0. And this is actually the moment of area. Moment of area, what does, like, here moment of area means? Let's explore this a bit. So what we are trying to say here is that the first moment of the member's cross section about the neutral axis must be 0. This condition can only be satisfied if the neutral axis is also the horizontal centroidal axis for the cross section. We have to recall here that the location of centroid of any cross section is defined from an equation that requires that the centroid lies on the reference or the neutral axis for symmetrical cross sections. Consequently, once the centroid for the member's cross-sectional area is determined, the location of the neutral axis is known. Now we can determine the stress in the beam from the requirement that the resultant internal moment M must be equal to the moment produced by the stress distribution about the neutral axis. The moment of dF in this figure about the neutral axis is actually dF into y, or simply dF, and dF is also equal to stress into d area, or actually differential area we have for the entire cross section. The total moment here, we have to take, for the entire cross section we have to take integral of this equation, and thus if we are taking integral again, we have come towards this equation which states that the ratio of sigma, or the maximum stress to the to C, I'll just call this variable as C, is a constant, and thus we are now having this integral which actually represents second moment of area. And we know that second moment of area about neutral axis or about centroidal axis is actually moment of inertia. So we'll replace this by the moment of inertia, and if we rearrange this equation, we have come up with this equation which states that maximum stress at any cross section is actually equal to moment at that cross section multiplied by distance from the neutral axis to the outermost fiber divided by I, or the I is actually, as I have already stated, moment of inertia of the cross section area about the neutral axis. Stress at any other location other than the outermost fiber can be determined using this equation, where we replace C by Y and apply a minus sign here to indicate that the stress will be compressive if we are moving uh, up from the neutral axis, and tensile if we are moving down from the neutral axis when the section is subjected to positive bending. Apply the flexural formula. The following procedure is suggested. First of all, you must determine the internal moment at the section where you want to find the stress. So for a simply supported beam, if you want to find the location of maximum stress, you will find it at the center point of the beam. After determining the internal moment, the next thing you need to determine are the section properties. So you need to determine the moment of inertia and the centroid for the respective section based on already established formulas for different sections. And then you have to determine normal stress using the equations that we have derived in the on the previous slides. We are we are in the most exciting section of this lecture, which is actually applying the formula to solve the real world problems. So in our first example, we are having a beam with a rectangular cross section, and it is being subjected to this stress distribution as shown in this figure. We have to determine the moment at the section that is caused by this stress distribution using the flexural formula, and then we have to determine the moment by finding the resultant of the stress distribution using basic principles. Okay, in order to apply the flexural formula, we know that we first need to know the moment of inertia. For a rectangular cross section, its neutral axis in the y direction or in the vertical direction is actually located at the center. I mean, this thing is very well known. So its moment of inertia has this formula bh cubed by 12, and we have this flexural formula here mc by I. We just plug in all the values here and rearrange the equation to determine that the moment that is actually causing the stress distribution is 24 kip feet. Okay, so now we have to determine the moment using basic principles. So basic principles mean that if we are having a stress distribution here, we can use the concept that we need to determine the average stress distribution, or you can say um, the area of the stress distribution, as stress distribution is triangular here. So this will be actually 1 by 2 into 6 inches into this intensity of 2 kip per inch square. This is very similar to something that we have done in previous lecture regarding the variational loading. So after determining the stress distribution for this triangular, you can say, area strip, we can then multiply it for this whole 6-inch strip as we are multiplying it here, and from this we have come over to this answer of 36 kip. In order to determine moment, we have to consider this fact here that actually a couple is acting here. We have a negative force or compressive force here, which is acting at the centroid of this triangular distribution, and we have a tensile force here, which is acting at the centroid of this triangular distribution. And since for a 6 inches triangle, this centroid will be 2 inch from the top and 2 inch from the bottom, so the distance between these two forces is actually 8 inches. So the couple arm is 8 inch, and thus we multiply the moment with this couple arm, and we have actually come up with this value of the moment. Sorry, we are applying the force with the couple arm. The force determined is 36 kip, and the product of couple arm and force gives us the moment, which is actually the same value as was determined using flexure formula in the on the previous slide. We have this simply supported beam. We have to determine the absolute maximum bending stress in the beam, and then we have to draw the stress distribution of the over the cross section. The absolute maximum stress in this beam will occur at the location of absolute maximum bending moment, which is the center point for this simply supported beam, as we already know. And using the basic principles of determining the moment, as we discussed in some of our previous lectures, we have come up with this bending moment diagram for the beam that states that the maximum bending moment in this beam is occurring at midpoint location with the value of 22.5 kilonewton per kilonewton meter. Now our next step is actually to determine the section properties, and here we are having a somewhat, you can say, complicated section, but it is not actually complicated if we divide this section into 3 rectangles here. Then we can determine the moment of inertia for this section simply using the parallel axis theorem. Okay, how can we apply this theorem here? Or the first of all, you need to determine the moment of inertia for these individual rectangles. For the moment of using the basic formula of bh cubed by 12, then you need to transfer this to the centroid of this cross section here. Plus AD square means you have to multiply the area of this rectangle with the distance between the centroid of this rectangle and the centroid of this whole section, which is actually at a distance of 150 mm here. And so 150 mm is from the bottom of this flange to the centroid, and plus 10 mm. 10 mm actually indicates the location of centroid for this rectangle, and thus we have our total distance d, which is actually equal to 160 mm. For this rectangle it is 160 mm, and for this rectangle it is also 160 mm, and for this rectangle its centroid actually coincides with the centroid of the cross section, so we are not having any kind of d for this central rectangle. And thus then by simply adding all these values, we have come up with this value of the moment of inertia of this cross section. Already know the moment of inertia, we know the distance from the neutral axis to the outermost point, and we know the moment of inertia and the maximum bending moment, and thus this is the value of the maximum stress. We also need to determine the stress distribution here, or stress at the location of point B here. So how can we do that? YB, or the distance of this point B here from the neutral axis, is actually 150 mm. So we can plug in this value in this basic flexural formula, and the rest of the things will remain same, the moment and the moment of inertia, and thus we have this value minus 11.2 megapascal. So the stress will increase linearly here from 0 here to a value of 11.2 megapascal here at this location point B, and then from 11.2 megapascal it will then further increase to 12.7 megapascal to this topmost fiber for this flange. Thus in this way we have determined the stress distribution along the whole cross section of this beam. So we are having this beam that is a fixed beam. Actually it is having a cross sectional area of a channel. We have to determine maximum bending stress that occurs in the beam at section AA. In order to determine again the bending stress that occurs at section AA, we first need to determine the moment that occurs at this cross section. Since this is a fixed beam, we can simply um just decompose this applied inclined force to a vertical and a horizontal force, and this the moment caused by this horizontal force can actually be neglected, and we'll mainly consider the moment that is being caused by this vertical force. But let's first consider the sectional properties of this cross section. Since this is a channel cross section, this is not a symmetrical cross section in the real terms. We are having a section of symmetry here, but this section is actually not symmetrical in this direction in which the bending is occurring. So what we need to do is first we need to determine the centroid of this cross section. For this we have to apply, or we have to consider this formula that in which we find the centroid for each of the individual components of a cross section, and then we shift them at decided, you can say, origin point here. So if we are having this like we have to multiply area, we are just considering this first, you can say, rectangle, this rectangle, this vertical rectangle. So its area is simple 0.015 into 0.2, but then for its the y bar is actually 100 mm. So we are considering it here at this bottom location. We are considering the zero location actually, or the origin at this bottom location. So the y bar, or the, you can say, the point of symmetry for this bar is actually 100 mm from this bottom. But for this bar, what will be the location of for this bar? It will be actually 110 mm, because the central point for this bar is here. It is 110 mm from the bottom. So this value is being reflected here. And this is simply area, and this means then we have summation of areas for these three rectangles, and thus we come up with this value 59.09 mm is the location of centroidal axis or neutral axis for this channel cross section. I made a mistake on the last slide. I said that will only consider the vertical force for the moment, but we are actually considering the horizontal force for the moment as well, because we have a channel cross section, and for channel cross section the neutral axis is located actually outside the cross section, and this horizontal force will also cause a moment in this cross section. The line of axis of this force is not passing through the centroid of the cross section. That's why it is causing a bending moment. And we need to consider this thing that based on the cross section of an element, the action or the nature of action of the force acting on it can change. So the vertical force, for the vertical force, the moment is simple 2.4 into 2 meter. 2 meter was the distance of the required cross section from the point of location of force. And for the horizontal moment, the force is actually the moment is actually 1 into the point of application of this force, distance between the point of application of this force and the neutral of the central axis, which was 0.059 meter as determined in the previous slide. And thus from this calculation we have determined the moment here as 4.859 kilonewton meter at a location of interest. Now we can determine the moment of inertia using same Miller principles as we have done in our previous example, and thus the maximum bending stress can be determined from the values of this moment of inertia and the location of the maximum fiber from the neutral axis, which was actually 0.1409 meter. We have reached the last example of our lecture. We are having a rectangular cross section that is designed to resist a moment of 40 Newton meter. In order to increase its strength and rigidity, it is proposed that two small ribs be added at its bottom. We have to determine the maximum normal stress in the member for both cases. So this is simple rectangular member, and this we can use the simple formula of moment of inertia to determine its moment of inertia. And then we have this simple flexure formula for determining the maximum stress that can occur due to this applied moment, which is actually 4.44 megapascal, a simple case. Now if we are attaching two ribs at its bottom, what will be the stress in this member? Let's see. Okay, now so we have now this rectangle with these two small ribs of 5 mm, and first of all we need to determine the centroidal axis for this changed cross section. How can we do that? Let's consider that we are having the neutral axis, the zero axis location, the zero axis or the origin, we are considering it at the top of the rectangle, right? So from this point to this neutral axis for this larger rectangle, y bar is actually 0.015 meter, but distance from this point to the centroid of this small rectangle is actually 32.5 mm. And using these values and the areas for the respective rectangles, we have determined this value for the centroid or centroidal point of this whole cross section. This value does not represent C. Instead, if we want to determine, you can say C is actually the distance from the bottom. So we need to subtract this value from the total height of this rectangular of this cross section, and thus now we have determined this 0.01908 meter. Using the parallel axis theorem, the moment of inertia about the neutral axis is, again using parallel axis theorem and this centroidal axis value, we can determine the moment of inertia for this whole cross section. Now we want to determine the stress at the maximum stress that can occur, and we know that the maximum stress will actually occur at this point and this point here, because they are furthest away from the neutral axis. Yeah, so now we have come up with this value of 4.65 megapascal. This value is actually more than the value that was determined previously. This means that in this particular case, addition of ribs to the cross section are actually increasing the stress instead of decreasing it. So we have come to this conclusion that any modification to a cross section or to an existing element is not always good. We should have a strong calculation basis to decide on such factors. With this note, I will end my lecture today. Thank you very much for listening. Any comments or questions or suggestions are welcome in the comments.